This is an online lecture to make up missing classes for the long holiday break for the next week. And I hope you watch this video before you come to the first class after our holiday. So in this video, what I'm going to talk about is the differential of multivariable function. And not only just differentials, I also want to talk about the differentiability of the multivariable function. And along the way, we're going to talk about the directional derivative, and partial derivative. And also, I'm going to talk about the gradient. And most importantly, I want to talk about the meaning of all these kind of derivatives. So what you have to remember after all this lecture and the consecutive next two videos, you need to understand the definition and the meaning. Of course, along the way, I'm going to give an example how to apply the definition to compute something and to apply something in the real life or some realistic situation, which will be covered in the second video. So I'm going to also talk about the project 5 about about visualizing the heat map. So that's for the second video. All right, so let me erase this and then let's start from the definition. So I'm assuming that we are familiar with the notion of vectors and also the notion of multivariable functions. For now, we're going to assume that our vectors are two-dimensional or three-dimensional, and all the functions that I've talked as an example of multivariable function is real-valued multivariable function, which means that it's either this type of function or this type of function. So the first one has two independent variables, and second one has three independent variables. And both functions has a value as a real number. Okay? That's for just now. After we talk about the differentiability of these type of function, I'm going to generalize the meaning or definition of the differential for general multivariable function, which sends n independent variable to m dependent variables. All right, so even for small period of time, let's just think about this function, two variable function. So this is the most simplest multivariable function you can think of. And I want to define, but before I define something, I think we covered this in the previous class, but I also want to remind you again that what I want is not giving you a new definition, but it's just extension of the meaning or definition of a derivative of a single variable function. So think about the meaning first. The meaning of the derivative, you can interpret the meaning of the differential of a single variable function in three different ways. One is rate of change, and the other is tangent slope, and the third one is by linear approximation. So when I say these three keywords, you have to be comfortable about what am I talking about, because we all covered this in class. But I'm going to give a little bit of explanation in this video too. So think about the rate of change. So I want to start from the definition. So given a function which is two variable function, so x y equals to z, and a point, two-dimensional point, x0, y0, and a vector. So in this case, we assume that it's a unit vector, meaning that the length of vector is 1. Let's say you can just call it u arrow, or you can still give some coordinates of this two-dimensional vector. So given all this information, the directional derivative of the function at the point with the vector is the value. So that's the important part. When we talk about the directional derivative, we are talking about a real number, which is a value defined by the limit when t goes to 0. You take x0 at y0 bt minus fx0 y0 here. And we denote that directional derivative as duf x0 y0. So look carefully inside of the limit. So we are taking the ratio of two values. The first one, t, is the parameter. So in fact, what we are doing is t minus 0. So we omit minus 0 here. So we are just looking at the difference between 0 and t. And look at the numerator here. So we are taking the difference between the value of functions at different points. So we are fixing the point x0, y0. So the only thing that changes when t is going to close to 0 is the value of the function on front here, which is evaluated at nearby x0, y0, but along the vector direction u. So here, let's say we have a point x0, y0 here. And here is my direction, the vector u. And we set this u to be the unit length. So if I move along this direction by 1 unit of length of the u, then I get some point. But you see, this point is x0, y0 plus tu here. So if you take up the position vector, then you can find the coordinate of the position of this point by taking the position vector from the origin to that point, by taking the position vector from origin to the fixed point x0, y0, and add t times u arrow here, u vector here. So let's say so t is small, then relatively the u might be this much long, but when I take t scalar multiple of u, then it will be shrink, right? So when t is small, it's quite less than 1, because we are taking t to equal almost goes to 0. So this point is where I take the value of function and then compare it with the value of function at the origin, and then find the difference and put it in the limit. So what am I looking at? We're looking at the rate of change. We are looking at the rate of change of value when I move my points along the direction of u. So that's why it's number, because it's the same thing as the rate of change of single variable function. So again, if I set my function's single variable function, large f of t, as f x0 at y0 bt, then this value, the directional derivative, is exactly same as f prime 0. So you see, the large ft is a single variable function. You can certainly take the derivative. You can find the rate of change of the function value at 0. And when you do that, it's the same thing as we did in the computation of directional derivative. We're looking at the difference between the value of functions at 0 and t, where t is very close to 0, but not 0. And that is same as the difference between the value of small f, and that's inside of the limit right here, and we're looking at the difference of t from 0. So remember this formula. This is the most important formula that you have to remember. And so So you have to remember this as a definition, because you always have to remember the definition. But more importantly, you have to understand why this definition came from. Why? Look at the first item here. So where did it start? We started from the first meaning of the derivative of single variable function. It was rate of change. So we want to make a similar meaning. We want to make up some concept similar to the rate of change, which applies to the two variable function, not single variable function, two variable functions. So in order to do that, this is the only way we can do it, because in the single variable function case, the rate of change is the relationship between the change of input, which is the real number, to the rate change of output, also which is just the number. But in the two variable case, the output in this case is just a number. The difference between the output is just the number. But difference between the input are not a number. It's a difference between two-dimensional points. If you have two different two-dimensional points, the difference is not given by a number, it's actually given by a vector. So how do we reconcile this difference between the single variable and second variable, two variable? So there's no way we can do it no way we can get the same idea of the rate of change of single variable case unless we fix a direction, right? So we have to fix the direction to make a difference of two different two-dimensional points into some kind of a change in values. So here we only change the value of t, which is the parameter. We fix the direction, but then by change of t, we take a different point from that fixed point. So now we get the difference between 2 points by just taking the difference between the difference of the length of this difference, right? The length of this vector joining 2 points. So that's the first meaning. And the definition of directional derivative. And let's move on to the second meaning of the derivative. So what do we want? We want to generalize the slope of a tangent line. However, there is no slope in the graph of the two variable function. So here, let's say we have a graph of two variable function inside of XYZ space. This is a surface, not a curve. So if I take a point and the point corresponding to the graph of the function, that doesn't have a unique line that touches the graph at that point. There are several, and there are infinitely many lines. So if we have to identify one geometric object that serves similar to what tangent slope does, tangent line does to the graph of the single variable function, it must be the tangent plane, not tangent line. So let's take a tangent line. Let's say this is my tangent line. So the meaning of tangent line also is purely geometric. So you can define it whatever way you want. But mostly we take the tangent plane to be the surface, or flat plane, which barely touches the graph or surface at that point only, right? So if you have a smooth surface as a graph of two variable function, then there's only one tangent plane that touches it. So let's assume that. And what we want is, we want to see what corresponds to the meaning of the differentials of two variable functions. So in this case, in the first case, in the single variable case, it was just the number which corresponds to the slope. But the slope as a number, a single number cannot determine the slope of a tangent plane, right? So in order to find out how tilted the plane is, you need to find out what the normal vector of this plane is. So let's call it n. So n, which is perpendicular to the plane at that point. Let's assume that this is also unit vector, okay? Because we don't care about how long this perpendicular vector is, as long as I know where the direction is. And also, I don't care about whether it's downward or upward. I just need one. And I want to find out what the coordinate of this n is. So how do I find that? Find the coordinate. How do I find one perpendicular vector that is perpendicular to this plane? So one way you can do that is taking two direction of movement of your fixed points. Let's say x0, y0 moves along x direction and y direction, which means that when you move along x direction, you're fixing the y value of the point. And when you're moving along the y direction, you're fixing x coordinates. So let's call it C1 and C2. So if I parameterize this movement, then C1t is x0 plus t comma y0, and C2t is x0, y0 plus t. And then let's do it one by one. When your point is moving along C1t, then the corresponding points on the surface will appear as a curve lying on the surface, right? Because you cannot deviate from the surface if you're taking the z value as a value of function. So it always lies in the surface, and it has to be a curve, right? Unless the function is linear. So anyway, so what we want is vector which is parallel to the tangent plane. So we want the instant speed or instant velocity at this tangent point along this curve, right? So let's say C1 tilde is lift up of the C1t. So the z value is there, but we can find the z value by plugging these two x and y coordinates into the value formula of f. So this is x0t and y0t. And let's call it v1. How do I find v1? I want the instant velocity of the movement of the point which follows along this C1 tilde. So v1 is C1 tilde prime 0. Why do I need 0? Because it's when t equals to 0 that I am starting at the point x0 and y0, comma z0. So how do I find the speed or coordinate of the speed vectors? You take the derivative of each coordinate. So each coordinate is a function of t. Of course, there's y0, which isn't t, where t isn't there, but still you can consider it as a constant function of t. So when I do that, the first one, x0 plus t, just the linear function, you get 1. And in the second coordinate, you get 0. And the third coordinate, you get what? You're taking derivative of a function which is only dependent on t. And you're moving your point x0, y0 along the direction of 1, 0, which is the unit vector parallel to x-axis. So you can call it as directional derivative of in direction of 1, 0 of the function f at x0 and y0. Let's call it this way. And let's do the same thing with the y direction of movement. So when I do that, I'll get some another direction of another curve which has intersection with this previous curve here. So let's call it C2 prime, which is the lift of this C2t on xy plane. And C2t is also given as x0 in this case, and y0 plus t now, because it only changes along the y. And z is f x0, y0 plus t. Okay. So what is the tangent vector here? So let's call it v2. It's the instant velocity of C2 prime. So v2 is C2 tilde prime 0. And you can take the coordinates by taking the derivative of each coordinate. So first one is 0, and second one is 1. And third one, it's the same thing, but you see the point is moving along y direction with the speed of 0, 1. So it's a directional derivative 0, 1, f x 0, y 0. Okay. By the way, so there are abbreviations, a nicer format of writing this kind of special directional derivative. So this directional derivative is called fx x0, y0. And this is also called fy x0, y0. And these are called the partial derivative. So once you have two vectors, two three-dimensional vectors, we can find the perpendicular vector, which is perpendicular to v1 and v2, which also serves as a perpendicular vector to the plane, which is given as n. So we can say n is the cross product of v1 and v2, which is given by 1, 0, f of x cross 0, 1, f of y. So of course, I have abbreviated all the notation is x0, y0 here, but you have to you have to think of this f of x and f of y, which is a number which is given by the directional derivative. Okay, so you can get a coordinates of three-dimensional vector n and look at what determines the coordinates. 0 and 1 are constants. It depends only on f of x and f of y, right? So the tangent slope, which is the meaning of the differential of single variable case, naturally generalized to the tangent plane, and what corresponds to tangent slope is the direction of tangent plane, and direction of tangent plane, which is determined by a vector perpendicular to that plane, is determined by the partial derivatives, right? Special kinds of directional derivatives. So at this moment, let's give some concrete example of doing this. So let's think about the meaning with the example. I'll give an example of a two-variable function here. So let's say f of xy is equals to xy plus y squared plus x squared. And my point is 1, 1. I want to find the tangent plane. What do I mean by that? I want to find the equation of tangent plane that is tangent to this point. So what do? We first need to find out the two tangent vectors which lies on this tangent plane. So first, v1, remember the formula? It was 1, 0, f of x, 1, 1, and v2, 0, 1, and fy, 1, 1. So I need to find out these two partial derivatives. So going again, f of x, 1, 1. So this is by definition directional derivative along 1, 0 of 1, 1. So how do we define? So it defined by limit when t goes to 0 of f of 1 plus t, 1 minus f 1, 1. So you see, I have 1, 0, so I don't have the plus t something on the second coordinates of this first term. And what do? We have a formula. We have a nice formula, so you just plug in there. So everything on the numerator will be just function of t, because I'm going to replace x by 1 plus t and y by 1. So let's do this. So we have t goes to 0. So t, and so we have 1 plus t times 1 plus 1 square and plus 1 plus t square and minus what? 1, 1. So it's a 1 minus 1 minus 1, right? So let's see, 1, 1 cancels out, and 1, 1, this one cancels out. And the last one, there's 1 plus 2t plus t squared. So we have t, right? So t survive here. T plus 2t plus t squared and divide by t. So I canceled out 1 and 1 in here. So what do we have? So we have limit of 1 plus 3. So it's 3t, right? So it's a 3 plus t when t goes to 0. So that's 3. So we know that this is 1, 0, 3. And how about this? So now I'll give you the trick to find out the partial derivative. So in the general directional derivative, there's no way you can compute without using the limit. But partial derivative, there are tricks. So just a small remark that so partial derivative f of x is given by taking derivative of f of xy as if, not true, but as if y is constant. And same thing is true when you take f of y. So you take x instead when you take fy as a constant, as if it's a constant. So for example, what is the partial derivative of fy here? So in this case, so when you have f of xy as this, when you take the derivative of y, you take x as if it's constant. So what do you do when you have constant multiple of y to take a derivative? It's just constant itself, right? So it's just x, and y squared is y squared. Y is not constant, so y is variable. so it's 2y. And how about x squared? So trick says when you take a partial derivative, you take whatever which is not the variable that you're taking the partial derivative with as a constant. So x squared is just constant, considered as constant. So it's 0. Okay. So that's a partial derivative, not the partial differential. So we have, we need to plug in 1, 1 here. So x is 1 and y is 1. It also is 3. So we get 0, 1, 3. So don't forget what we are doing here. We want to find the equation of tangent plane at this point of this function graph. So we want to take the cross product of these two three-dimensional vectors, 1, 0, 3, 0, 1, 3. So the cross product v1, v2 is given by determinant of e1, e2, e3. So e1, e2, e3, again, it's a three-dimensional vector, which is standard vector 1, 0, 0, 0, 1, 0, and 0, 0, 1. And we have 1, 0, 3, 0, 1, 3. And what do we have? We have minus 3, and we have also minus 3 and 1. So it's not unit vector yet, but really doesn't matter if you take the unit vectors or not. But since I mentioned it's unit vector, I'm going to take the division of its size. So when you take the length of this vector, 9 plus 9 plus 1, so 19. So again, you can get a square 19 of minus 3, 1. Okay? So that's your normal vector. So what do you do when you have a normal vector to find the equation of the plane? So let me erase this part and maybe, okay, so I can erase this part. So once you have a normal vector, perpendicular vector, you can find the equation of plane like this. So you have a point 1, 1, 3, which passes through the plane, which is lying on the graph. And since we know that the tangent plane, this plane is tangent plane, which passes through the tangent point 1, 1, 3, that's the point that definitely know that lies on the plane. And let's say this is x, y, z, an arbitrary point on the plane. We want to find out how these three coordinates are related. So only way I can find the relation is that if I take the vector pointing from here to here, we can call it position vector, it must perpendicular to the normal vector of the plane. So what's the vector pointing this from this point to this point? This is x minus 1, y minus 1, z minus 3, right? So since these vectors must be perpendicular to each other, when I take the inner product with n, it must be 0. So you see, if I write down this again, x minus 1, y minus 1, z minus 3, inner product with what? Minus 3, 1 divided by square root of 19 equals to 0. So here, square root of 19 doesn't really matter whether or not you have it. It's not going to be changed the equation itself. So that's why I said you don't really need to normalize the vector n. But anyway, so let's erase this out. And what we have? Minus 3. So take the inner product between two three-dimensional vector. X minus 1, minus 3, y minus 1, minus plus 1, z minus 3 equals to 0. So that's your equation of a tangent plane, okay? So along the way to find the tangent plane through this example, I also mentioned that how to find the derivative as an example of the directional derivative, and also how to find the partial derivative as a kind of a cheating way. So I'll tell you why this is cheating. The remark I mentioned above, I'll explain why this is kind of cheating, because this actually gives wrong answer if you applied in a very different situation. This applies with a very important condition, but I didn't say that what condition is. All right, so we so far covered two meanings, two keywords, which can be generalized to the meaning of the differential of the second two-variable function, right? But there's one more definition, and actually we didn't explicitly say that what is the differential of a two-variable function. We only just generalized the meaning. I mean, we talk about our thought about how to extend the meaning of the differential of the single variable function to the meaning of the differential of a two variable function. So here, let's think about the third one. So this is the part that I didn't cover in the last class. So we have to be careful, pay attention very carefully here. So it's about linear approximation. So when we say f is differentiable at x equals to a, let's say I'm talking about the single variable case. So let's say f of x is differentiable f of x a, it's differentiable at x equals to a. This, by definition, is equivalent to say that 0, the limit of this thing is 0. So when x goes to a, x minus a, xx minus lx, where lx is f prime a plus times x minus a plus f of a. Why? Well, actually, I said it's equivalent to the definition of differential f prime a. It's right here. So in order to find what lx is, you need to find f prime a. And if you know what f of a is, then you can always say that by definition of f prime a, using the limit, you can say this is true. So we want to extend this meaning. So let me give a definition here. A two variable function fxy is said to be differentiable at x0, y0 if there exists a linear function Lxy. So what do you mean by linear? What do you mean by two variable function Lxy is linear? It means that it's a polynomial function of top degree 1. So you can have 0th degree, which is let's say a, and you can have a first degree term, which is b, let's see, just b, and also you can have another first degree term in terms of y. So the Lx here, meaning that it's linear, means that it always has to be of this form, a plus b plus x plus cy, a, b, c being just real number, such that, so it's not over. So I just said that there should be some linear function satisfying that 0 is equals to this limit. So when x and y is converging to x0 and y0, we want x minus x0 square, y minus y0 square, sum square, and the difference between xy and lx. So that lx, this lx, being equal to 0 when you take the limit. So what is the keyword here? We are defining whether or not a function is differentiable. So we call it differentiability of a function. So we are defining when this function obtains a differentiability at certain point. It's only when you take this kind of limit equals to 0. So where does this kind of limit come from? It assumes that we can find such linear function with a specific coefficient a, b, c. So we can infer some kind of information what a, b, c must be here. So when you take the limit of these two things, look carefully what the denominator becomes. The denominator is actually the distance between point xy and x0, y0. You see, this is just the Pythagorean theorem that x0, y0, xy and x0, y0 different, the distance between these points. So denominator always goes to 0 when xy goes to x0, y0. So if you have some limit here, then there's no way other than this numerator goes also 0. If numerator doesn't go to 0, then denominator goes to 0, so the limit must diverge. So being equal to 0 means that your numerator must be 0 as x0, y0, xy goes to x0, y0. So now I can erase this part. Think about that case. which is kind of dirty. So think about what does that mean. So we know that x, y goes to x0, y0, that the limit of the Lxy must be fx0, y0. We know that this must be true, right? Because we definitely know that f of xy is going to fx0, y0. Oh, by the way, so we have a, if you want to throw in more condition here, then you have to throw in that function f of xy is continuous at x0, y0, but it's actually immediately follows from the definition here. But anyway, so since we know that the function xy is converging to fx0, y0, the Lx, whatever that is, must also converge to fx0, y0 when xy is converging to x0, y0. So look at this formula. We have already have a specific form of this linear function. So if I plug that in, so a plus b x plus c y, the limit of xy being x0, y0 must be this. And the linear function is already a continuous function. So when I take the limit, I can just plug that in because that's the meaning of that's the definition of continuous function. So a plus b x0 plus c y0 must be f x0 y0. So I can at least know that a must be f x0 y0 minus bx0 minus cy0. So now what we can say about L. So I can get rid of A in terms of BC. So Lxy is just f x0, y0. And let's combine B part. So we have B x minus x0. And we have C part, so y minus y0. So your Lx must be of this form. We don't know what BC is, but we will find out what BC is shortly. So anyway, the linear function, linear map, or linear function L must be of this form. And again, we can think of this limit definition further. So if you really have the differentiable function, it means that this definition requires us that this equality is true, no matter what path xy is taking to get to x0, y0. That's the meaning of the limit. Having a limit for two-dimensional points approaching to one or to another fixed two-dimensional points, that means the limit must be the same no matter what kind of path you take for x, y to get to x0, y0. So let's say I want to take a path, two specific paths from to get to x0 and y0. So let's say, let me draw this thing here. So we have x0, y0. The one special path that I can take is I can get to x0, y0 horizontally. So let's call it C1. And another path is C2. So that's not all the path, but I just want to take the two special cases and see what happens about the limit. So the first path says that so again, C1 and C2 is the same path I took when I talk about the different directional derivative. So I don't have to write the coordinates here. So the limit can be written as, so in the C1 case, when t goes to 0, what happens to the denominator? So t is the parameter inside of the parameterization of C1, which goes to x0, y0 horizontally. So when t equals to 0, I get to that point. But when t is not 0, then I'm maybe in the left or right. But look at this. Y is not moving, so y minus y0 is always 0. And how about this? X minus x0. So it's t, right? So I'm just moving t away from x0. So the t squared square root. So maybe you can say t absolute value if you want to. But you can also assume that t is positive by taking t is being positive and get to 0 from the positive direction. So you can just ignore the absolute value sign here, just call it t. And look at the numerator. So I have that x is x0 plus t, and y is fixed at y0. And I know that the formula of L is given by this. And the C part, the y is not changing from y0, so you can just ignore this. And only what left is these two, and I know that x minus x0 is just t. So we get f x0 y0 minus bt. So what do we have? So you can take split this quotient here. So we get t is going from positive to 0, and we are taking the ratio between the difference of function value and t, and then take minus b. So I canceled out t here and here. Okay, so that must be equals to 0 if this is true. So I'm talking about what b and c must be if I know the function is differentiable. So by taking C1 path, I know that b must be this. Right? So what is that? So I'm taking the difference between the value of function when I move my x0, y0 away from that point in the direction of 1, 0 in the x direction, right? I told that that's the directional derivative, and it's a special kind of directional derivative called partial derivative, and it's the partial derivative in terms of x because I'm changing the x coordinate only. So this is same as f of x, x0, y0. The same thing happens when you compute with C2 path. In the C2 path, now B part disappears, C part remains, and the C must be Fy x0, y0. So in fact, so whenever you want to check whether function is differentiable at the point or not, is what you want to go for the linear function L is that the A or the formula of this L must be f of x0, y0 plus f of x, x0, y0. Sorry, erase this part. And x times x0 and fy, x0, y0, y minus y0. That's your linear function. That must be the linear function inside the limit in order to check whether it's 0 to conclude that it's differentiable at that point. So I'll give you the example. So here, it's a bit different notion. So you have to distinguish these two concepts. One is the directional derivative. And the other is differentiability. So in the first part, in the just before I talk about this, we talk about the directional derivative or partial derivative as a special case. And now we're talking about the differentiability of two-variable function. So they are not the same thing. They are different concepts. They're not the same thing. But they're not completely different because you see in the definition of two-variable function being differentiable, there is some in overlap between the meaning between the directional derivative and this linear function, because we need the partial differential in order to find the formula of the linear function, right? But you have to make sure that these are not the same concept. So again, we only talk about the differentiability, so I'm going to give you the example of differentiability of a function. So let's say our function f of xy is x squared plus y squared sine 1 over x squared y squared when xy is not equals to 0 and 0 if xy is equals to 0. Show that fy is differentiable at x0, y0. Okay? I'm not talking about finding directional derivative. I'm not talking about finding derivative because we didn't even talk about what the derivative is. We only talk about whether it's differentiable or not. Okay? By the way, in Korean, differentiable is 미분 가능. It's not 미분. 미분 is differential. Differentiable is 미분 가능. Okay? So how do we show that? Of course, so we need to find out whether there is a linear map, linear function satisfying this equation. Okay, so suppose Lxy is equals to 0. So it's a constant function whose top degree is 0, but still it's linear. It just means that the coefficient of first order and first degree terms are all 0. So we can just take this as a linear function. Then the limit, let's count the limit. Let's compute the limit. What happens when xy goes to 0, 0? So we have x squared, y squared, just take the two definitions here. And then fxy and lx is just 0. And what is the limit? So I'm taking a square root here, and you can and also xy is approaching to 0, 0. It's not equal to x0, 0. So I'm not taking x equals to 0. I can take this equation. I have to take this formula for f. So I have x squared, y squared, sine 1 over square root x squared, y squared, divide by square root x squared, y squared. And what happens? I can cancel this out, right? So I'm looking at the limit of this formula as xy goes to 0, 0, 0. So you can see that the sign is oscillating infinitely many times as xy goes to 0 because it goes 1 over 0, which is infinity. However, the amplitude of this oscillation is getting 0. It's getting smaller and smaller. So even though there is infinite oscillation, the overall size of this value will go to 0. So we know that this is equals to 0. So what we showed here, we showed that this equation in the definition is true for this L. Okay? I don't even have to compute the partial derivatives. All I need is there is some linear function that satisfies this equation. To conclude, the function is differentiable. So this is differentiable. This function is differentiable. So if you draw this function as a graph or a surface in 3 dimensions, there is lots of oscillation. So it's kind of a wave in an ocean. But since the size of this oscillation is getting smaller and smaller, so you get the almost flat surface around 0. So even though there is a tiny amount of oscillation. Anyway, so before we talk about what is the derivative of this function, I want to talk about the meaning of the differentiability. So differentiability, or function being differentiable, is saying that the limit of this ratio goes to 0. What does that mean? The ratio is basically 0 over 0, right? That's what that's what we agreed here, because denominator goes to 0, numerator must also goes to 0, but it says the limit itself is 0. Therefore, the numerator must go faster to 0 than the denominator. Otherwise, there's no way it can go to 0, right? So if it goes to 0 at the same speed, then it cannot be goes to 0. It could be 1 if the speeds are the same, 2 or 3 if the speeds are that proportional ratio, but it says it's 0. So the speed of this error between the function and these two functions goes to 0 is much faster than the speed of this thing goes to 0. And this thing represents, again, the distance between the point xy and x0, y0. So you can say that the function is differentiable if the approximation of the linear map, there is a linear map, linear function, which approximates the value of function, and the error goes to 0 much faster than the speed of the point xy goes to x0, y0. Okay, so in other words, this L is a very good approximation because it's better than the error is better than the difference between the point around x0, y0. So we call this L a good approximation. That's actually a technical term. So we can say that Lx satisfying this equation as good approximation, and with that terminology, you can say two-variable function is differentiable if there is a good approximation. So, what does that mean? I said in the words about this limit, but what does that really mean? Well, when do you not have good approximation? So think of this way. Let's say our f of xy is slightly different from this formula, x squared plus y squared. So imagine you want to find out the L or with that L, the limit is equal to 0. The problem is, can you find anything like that? Can you find such L? So let's try to find that. Let's try to find whether there is such L that satisfies the equation that requires by the definition of differentiability. So if there is such L, as we said, L must be determined by the partial derivative as a coefficient of the linear terms. So we'll first find out what f of x 0, 0 is. Let's try to compute. So by definition, so here is one good example that you cannot apply the trick to find the partial derivative by taking other variable as if it's a constant. So because when you do that, you're not gonna be able to plug in 0 and 0 in here, right? So we have to follow the definition of partial derivative. So how does the partial derivative of x defined? It's the directional derivative with the direction of 1, 0. So it's when t goes to 0, t f, and so x0, y0 is 0. So I only have t0 and f0, 0. So what is it? So I have ft0, and when t is not equal to 0 here, so so this is only a case when x and y are both 0, so I have to use this formula. So I have t0, so we have t, so I can take t as a positive value here, the t sine 1 over t, right? And then divide by t, so it cancels out each other. I have this, right? So what is the limit? Limit doesn't exist. Limit doesn't exist. It's not even 0. I mean, it's so there's nothing here, right? Because sine is oscillating from -1 to 1. There's amplitude is still always same as 1. The same for fy0, 0. So you cannot find the partial derivative, which means that you cannot find L, because if there is such L, then we already showed that the coefficient of the first degree term must be given by partial derivative. So being the partial derivative being non-existence means that there is no such L. So what do we conclude here? F is not differentiable. F is not differentiable at 0, 0. All right. So now, what can we say about? So these are very special cases. These are specially designed to show you that the differentiability is not always satisfied. So in most cases, for example, if you're dealing with the polynomial functions or exponential function, you can always find the function as differentiable function. So now we want to talk about what is the differential or derivative of two-variable function. So when you have a differentiable function, for instance, in the single variable case, you can always find its derivative or differential, right? So we want to do the same thing. What's the differential of derivative of two-variable function when it's differentiable? So let me define it this way. So we're going to talk about the gradient first. Gradient of two-variable function at this point is the two-dimensional vector given denoted by nabla f. This upside down triangle is called nabla at x0, y0, whose coordinates are fx and fy. So it's a two-dimensional vector. So it's called the gradient. And let's give another definition. If the function f of x 0, y 0 is differentiable at x0, y0, then the differential of f at that point is first denoted by df x0, y0. D stands for differential and is given by 1/2 matrix, but whose coordinates are same as the coordinates of the gradient. Okay, so there's a reason why I gave the definition of gradient. First, the gradient and differential for two-variable function case is almost same, because you can call this 1/2 matrix as if it's just a vector, because it only consists of two entry and it's linear. I mean, there's no two-dimensional array. It's just one-dimensional array of numbers. And also, if you have a matrix, it satisfies all the operations of vectors. You can add two vectors, two matrices of the same form, and you can also take a scalar multiplication. So as information-wise, there's no difference between gradient and the derivative. But the meanings are different. Meanings are different. But here, I'll give you the connection between these two concepts here. So this is also the most important part. Also, we are extending the meaning of the linear approximation here, but here's a different way of doing this. So fourth meaning, another meaning that I didn't mention yet, is that our derivative is a map that relates the difference or changes in input and output. So think about the meaning of the differential of single variable function. What does that do? So in remark, if you think about the f prime a, then you kind of know that it's almost similar to the change of y over change of x. So it means that if you rearrange these terms, delta y, which is the change of y, can be approximated by some multiple of changes of input. That multiple is the differential of the function, right? So in other sense, this differential is kind of a map that maps the changes in input to the changes of output, right? So whenever you think about a map or function, it's just the relation that sends one value to another. So this is a map that sends a value which represents the changes in x from x0, or a, sorry, it's okay, a, to some value which is represented with changes of y accordingly, right? So it's a map. So we want to do the similar thing with the two-variable function. So think about the case here. When you look at the definition of differentiability, I'll rewrite this again. So x, y, x0, y0 here, and blah, blah here in the denominator. So what we have here is xy minus x0, y0. I'm going to write down the formula of L here again, and minus f of x, x0, y0, x minus x0 minus fy something, y minus y0. So it's going a little bit outside, but that's okay. I'm going to write it again here. So only the denominator, only the numerator part. So here f of xy is minus x0, y0. And so how do you write this? So you can write down this value, f of x minus something, as the following matrix multiplication. So we have f of x, x0, y0. I think I need more space. So let me write it down one line below here. So minus f of x, x0, y0, f of y, x0, y0, and multiplying. No, this is 1 by 2 matrix. The next one is 2 by 1 matrix given by x minus x0, y minus y0. So you get the same formula, fxy minus lxy, by doing this, right? So what do we have here? So this is the numerator of the equation that we had in the definition of differentiability, and it's about the difference in difference in the value of function. So it's basically difference in z values, right? And if you see a little bit closely here, you get the derivative, the same derivative right here, defined as 1 by 2 matrix here, appeared here, and you have 2 by 1 vectors again. So you can also say this is same as minus df x0, y0 times what? x minus x0, y minus y0. Right? So what does this value mean? Only this part. What does this value mean? So this part, okay. I mean not this part. So just this part. Okay. So fxy0 is the starting point of your z value. That's the starting point. That's the base value. And you moved your value of function a little bit. So the actual value is here. So this is actual value. And you want to kind of estimate, you want to approximate how much your value were changed, but not by looking at the real value of function. So it's right here, but you want to estimate by the linear function you defined earlier in the definition of differentiability, and that's Lx. So how does you define the Lx value? You start from the base value, so that's the base. That's known because we know where to start, x0, y0, and you want to add the changed value. So that's your approximation of change, right? That's your change of z, right? So, I mean, approximate change of z, right? So it says, so if I say it differently, delta z, which is the change of function value, is approximately given by matrix multiplication x0, y0 and minus y0. So you can think of this as some kind of a map that relates the difference in the input values. So here value is not number, it's the position of 2 points, right? Difference of positions in 2 points. So the difference in vectors, or the vector itself, is the input, change of inputs. And then this map, this matrix, by matrix multiplication, maps these changes in input from xy to x0, y0 to the changes in the z value. So it also serves as map that sends these two-dimensional vector to one-dimensional vector, or just the value. the changes of inputs to changes of outputs, which is the value of function. So that's one way you can think about why this the derivative is defined by 1/2 matrix. So if you want to relate, so there's no other way. So it's natural, very natural. So if you want to relate the changes of input to changes of output, when the input is vector and the output is just value, think about the value as 1/1 matrix. So here again, df xy0 is first you take changes of inputs here. So changes of input consists of changes of x coordinates and changes of y coordinates. And then you map it to changes of z coordinate, which is the dependent variable, right? So this is a two-dimensional vector. And this is one-dimensional vector. So you want something, you want some mathematical object that relates two-dimensional object to one-dimensional objects. What it does is the matrix. When you take a matrix multiplication, you want 2/1 matrix goes to 1/1 matrix, so it's 2/1, and this is 1/1. What matrix you have to multiply on the left of this 2/1 matrix to get the 1/1 matrix? So if you have 2/1 multiplied with something by something to get 1/1, there's no other way to get 2, because that's where you have to get where you get a validated matrix multiplication, and you also have 1, right? So 1/2 is multiplied by 2/1 to get 1/1 matrix. So you need 1/2 matrix. That's this matrix. That's given by these two coordinates. And the reason why you should get this partial derivative as an entry of 1/2 matrix is very natural. It comes from the differentiability. It has to be that two partial derivative in order to make a meaning out of these limits. You want to relate the difference in z values in difference in the input values, right? And also you can talk about the same thing with the gradient vectors, but actually it's more direct here. So you can also talk about the same equation in the definition of differentiability as follows. So 0 is equals to x comma y goes to x0, y0, and blah, blah, here. So we have x, y minus x0, y0. And the part that I have here can be written as minus of gradient x0, y0 inner product. So this is inner product with x minus x0, y minus y0. Okay, but you get the same meaning. So this is the actual changes in z value, right? So in that case, you can also say that the gradient vector serves as, so it's a vector, by the way, it's a vector, but it can serve as the map that sends the changes in inputs, right? This is the changes in input to the changes in output, right? So in a summary, so memorize the definition of derivative. That's the first step. You have to memorize the derivative and the definition of derivative, differentiability, and the gradient all separately, okay? But also, you need to have a good intuition which unites the meaning of these three definitions, which is differentiability or derivative. Derivative is a map that relates the difference in inputs to the difference in outputs. So what do you mean by difference in inputs? It depends on what your input is. So if your input is number, then the difference of input is also one number. But if your input is point, then what's the difference of inputs? It's a vector, because you want to see how much one point is moved away from another point. The only way you can find out the difference in that way is using the vector. So if your input is three-dimensional vector, the difference in three-dimensional vectors is three-dimensional vector. And if you have two-dimensional points, then the difference between these 2 points is two-dimensional vectors. Okay, so I'm gonna show you lots of theorems. I'm gonna conclude with the theorems, which also add to your, maybe help to your the understanding, to get a nice, better understanding, better understanding of these concepts here. All right, so theorem first. If so, here again. Oh, maybe I okay. Before I move on to the theorem, okay. So let's talk about the theorem, and then let's finish with the generalized definition of differentiability and derivatives. Okay, so theorem. So if f is differentiable at x0, y0, then f is continuous at x0, y0. So you have same theorem for single variable case, but that's true for two variable function too. So why is that? I cannot prove everything, but this is simple, so I can prove it. So being differentiable means that we have x, y goes to x0, y0. The distance between x and y, let's say x minus x0, y minus y0. The size of this vector is in the numerator, a denominator, and we have f xy minus l xy, right? So what is L? So here, Lxy must be the linear map, and it must goes to Lx0, y0, as xy goes to x0, y0, right? And then, what if that's true, then there's no other way than f(xy) goes to fx0, y0 in order to make the numerator become 0, right? So therefore, has to go to x0, y0 as xy goes to x0, y0, because the numerator, or the function here, minus Lxy, must go to 0. Okay, so that's the definition of proof. So you don't need to assume the continuity to define the differentiability. All right, so the next one. So if f is differentiable at x0, y0, then the directional derivative exists for all direction. That's also easy. Why? Let's call it this way. So if I take special direction of movement of my point from x0, y0, then that's u. Then all I can do to find the derivative, or make the equation to be equal to 0 in the definition of the differentiability, is that I go make t goes to 0, and the t up here. Well, let me write it down right here. So it's gonna be the size of what? x0 at minus x0 y0 plus bt minus y0. So I'm assuming that u is coordinate AB here. And you know why I'm using this? So you should not think awkwardly if I use this denominator as the norm of a vector, because it has the same formula as in the definition, right? So I'm just using this because it's cleaner than using the square root. So what is fx0 plus at and y0 plus bt minus L. So L, since we assume that it's differentiable, so I can write down as fx0, y0 minus fx. So just writing down the formula of L, x0, y0, and now I have x minus x0, but x is x0 plus at, so I can just say a times t, and minus fy x0, y0, bt, right? So I'm doing this, and what's the denominator in this case? The denominator is just x0 cancels out, and what we have is a comma b times t. So we know that a comma b, or the coordinate of u, is the size of u is 1. So if you take the square sum, then it's 1. So all we have is just t, right? So this is same as 0 equals, so just equals to t goes to 0. And also I can assume that t is going from positive direction. So we have limit of t. And then we have t in the numerator and fx0 at comma y0 plus bt minus fx0 y0. So far, so good. And now I can get rid of t and cancel out t in the bottom and above here. So in that case, I have no t at all after that, canceling out t. So I can get the terms outside the limit. So it's minus a fx x0 y0 minus b fy x0 y0. So that thing, entire thing, is equals to 0, right? So now let's move this part to the right left-hand side. So what do we have? Then I can get rid of this and then this. This limit is same as a fx plus b fy. Okay? So what is this part? The limit. What is this limit? This limit is the directional derivative. This is what we call duf, x0, y0, right? So this says the differentiability, it comes from the differentiability because that's the only equation we used. It says that the directional derivative is same as given by this formula, which also only uses the coordinate of u and the partial derivative. So we can also say that it's u inner product with gradient f, right? Because the inner product, this is the formula of two inner product between two vectors. So the theorem not only shows you that this is true, I mean, directional derivative always exists because u is given and the partial derivatives are given because it's differentiable. Also, it gives you the formula of a directional derivative. So let me write down the formula here again. The duf x0, y0. This is your formula. I mean, that's not definition. Definition is separate. You can find the directional derivative if the function is differentiable using this formula. Okay, so the third one, third theorem, is that, so you might wonder, okay, so I know what happens when it's differentiable because it's these two theorems tells you what happens when you are having a function which is differentiable. But when can I say that function is differentiable? What is the sufficient condition of the differentiability? So here is the theorem. So if fxxy, fyxy are continuous at x0, y0, then xy is differentiable at x0, y0. So again, there are something that I didn't mention. There's a concept that I didn't mention yet, which is the derivative, partial derivative. Okay, so what's the difference between partial differential and partial derivative? Partial differential is 편미분 계수, and partial derivative is 편미분, right? So partial differential is a number. So these are partial differentials. So these are partial differential. Okay? And these are partial derivative. What's the difference? partial derivative is a function. It's a function that has a value as a partial differential, just like the derivative of a single variable function. Okay, so the theorem says you can make a partial derivative as a function whose value is partial differential, and if you find that these two variable functions are continuous at x0, y0, which means that you can find the value of partial differential at every nearby points of x0, y0, and then these values are continuously changing around x0, y0. That's the meaning of continuity here. Then your original function is differentiable at the point. So you think a little bit puzzled here in this case. So if you don't have a clear distinction between the partial derivative and the derivative itself, you might be really puzzled by this, because, okay, so we have a partial derivatives. We already have a partial derivative. But then why do we need this extra condition to conclude the function is differentiable? So here, we're not talking about the differentiability of a function. We only are talking about whether we can take partial differentials or not, and if the partial differentials are changing its value continuously. So partial differentials is nothing similar to the differentiability we talk about. They are different concepts. That's what I emphasized in the middle of this lecture, that directional derivative is not the same as the derivative or differentiability. So in fact, the fact that you can conclude the differentiability of a function purely by analyzing the behavior of partial derivatives are very striking fact, because they are totally different, but there is a very close relationship between these two. If you have a nice behavior of partial derivative, which is continuity, then the theorem says it's differentiable. So it's a bit harder to prove the theorem, so I'm gonna just skip this out. But so I can give, so these three theorems are, so let's see, 1, 2, 3. Yes, these three theorems that you can use it, but you have to use it with cautions that sometimes you might say converse to this theorem and still the fact could be true, but it's not always true. The converse any of this theorem is not always true. For example, there is a function which is differentiable, which has no continuity of the partial derivatives. So the converse could be false for some example. And also here, there is a function which is continuous but not differentiable. And also here, there is a function whose directional derivatives directional derivative exists for all direction, but still the function is not differentiable. Okay, so I might go over this example if I have time, or after the long holiday break. Some people are not confused and not convinced about the theorems and still want some ideas. Then I can go over with examples. But also, these things that I covered today are all in the book, our textbook. So please read through the textbook if you're not convinced yet. Or also, you can rewind the video again to look carefully, listen carefully what I did here, and then try to make sense out of your own language, and then see if you can make any sense, or if you're stuck, and write down where you're stuck, which concept you're stuck at understanding. All right, so this is the first video. So let's call it here. I'm gonna upload a second video soon, and have a good holiday.